Welcome to the Robotics Brief. I'm Alex.
And I'm Sam. Glad to be here with you.
So, Sam, we've got a batch of papers today that really make me wonder if the whole concept of edge computing, as we've understood it for the last 5 years, is becoming obsolete before it even properly took off.
That's a strong take. You think the edge is dead? What are you seeing that suggests that? I mean, we're still talking about putting more intelligence closer to the data, right?
I am. Because it seems like the defining characteristic of a lot of these new approaches is this profound, almost obsessive focus on efficiency, but not necessarily efficiency at the very furthest edge. It's about getting more out of less wherever you are, pushing the limits of what a single GPU, a single phone, or even a basic CPU can achieve.
So it's not about the geographic distribution of compute. It's about the density of computation in any given unit, because that feels like a subtle but important distinction. I think a lot of people conflate edge with low power and low capability.
Exactly. It's less about moving data to the edge and more about making whatever compute you have, whether it's a server farm or your pocket, so much more capable that the traditional constraints of edge versus cloud start to blur. It's about localizing power, not just localizing data.
All right, let's dive into some of that then. What's our first example of this paradigm shift, Alex?
Well, speaking of making a single unit perform feats, let's start with Terra Zero, procedural driving simulation for zero demonstration self-play at scale. This one's wild because it talks about running a driving simulation not on a massive cloud cluster, but achieving 1.3 million agent steps per second on a single server-grade GPU.
Okay, 1.3 million steps per second is insane. Seriously, that's a speed that makes previous simulators look like they're crawling. And it's all CPU for simulation, GPU for policy inference, zero copy path. They've optimized every millisecond out of that process.
They really have, Sam. The goal here is to train robust autonomous driving agents, and they need speed, realism, and diversity. That speed, for reinforcement learning, means they can iterate through scenarios so quickly it's almost hard to grasp. It's an order of magnitude shift in what's possible on relatively contained hardware.
My question, though, is how realistic can a procedural driving simulator be? You're generating the world, not rendering a pre-scanned environment. That diversity is crucial for safety-critical long-tail events, sure. But what about the subtle, nuanced cues of a real city? Can it capture the messiness of actual human infrastructure?
That's a fair challenge. They claim it's realistic enough to ground behavior in real-world map structure, but you're right, the devil's in the details there. What I find compelling is the combination of procedural generation for diversity and then this almost unbelievable throughput on a single piece of hardware. It fundamentally changes the economics and accessibility of large-scale autonomous driving research.
It does. It moves the bottleneck from compute availability to, well, algorithm design and good data curation within the simulation. I still worry about sim-to-real transfer with purely procedural environments, though. The physical world has a chaotic elegance that's hard to procedurally generate without losing critical nuance.
And yet, Sam, if you can run a billion scenarios overnight, the chances of stumbling upon those nuances, or training around them, dramatically increase. It almost makes brute force viable.
It's an interesting trade-off, isn't it? Speed versus fidelity. They're clearly banking on speed winning out for broad generalization.
Next up, let's talk about efficiency in a different way, Sam. Do AI agents know when a task is simple? Toward complexity-aware reasoning and execution. This paper is a direct jab at LLM agents that just churn through everything with maximum context, rereading files, turning a one-line edit into a full codebase audit.
Thank God. This is something I've been shouting about for a while. LLM agents are incredibly powerful, but they are also profoundly stupid about resource management. They just read everything again, every single time. It's like they're allergic to caching their own memory.
Exactly. The authors are calling for task-aware execution scope estimation, which means judging a task's difficulty, knowing what information it truly needs, and finding the shortest, most reliable path before committing budget. It's about formalizing minimum sufficient execution.
Look, this is critical, Alex. If we're going to use these agents for multi-step engineering and informatics workflows, they can't be burning through GPU cycles and API tokens like they're free. The environmental and financial cost alone makes that unsustainable. It's inefficiency at its core.
Right. And it's not just about cost. It's about speed and responsiveness. If an agent takes 5 minutes to reread an entire repository for a one-line change, it breaks the flow of interaction. It makes the agent feel slow and cumbersome.
Yeah, and it's also about reliability, isn't it? The more context you feed these models, the more opportunities there are for them to hallucinate or get confused. A shorter, more focused execution path should, in theory, be more robust.
You'd think so, wouldn't you? It's almost a back-to-basics approach for agents, focusing on the fundamental problem of knowing when to stop gathering information or when not to gather it in the first place. It's a foundational piece of intelligence that somehow got overlooked in the race for bigger models.
It did. It's like they built a super powerful car and then forgot to teach it how to change gears efficiently. This feels like a very necessary correction.
From efficiency in thinking to efficiency in doing. Dense reward. Dense reward learning via failure synthesis for robotic manipulation. This one's about improving reinforcement learning for robots by generating failure data synthetically instead of needing humans to laboriously collect it.
So instead of having a human repeatedly make the robot mess up, they're basically creating pseudo-failures to teach it what not to do. I like the sound of that. Collecting failure data for robot manipulation is notoriously difficult and time-consuming.
That's right. The challenge with RL and robotics is getting reliable, dense, and informative feedback. You need a lot of diverse failure data, but collecting it manually is a nightmare, and relabeling successful demos as failures often doesn't capture the real problem space.
Yeah, it's like trying to teach a kid not to touch a hot stove by showing them a picture of someone not touching a cold stove. It's not the same thing. So how are they synthesizing these failures? Is it just random perturbations? Because random doesn't always equal informative.
They're using a novel approach that focuses on what they call failure synthesis. It's not just random. It aims to generate diverse failure types that are representative of real-world problems. The paper talks about overcoming the challenge of acquiring diverse failure data at scale and obtaining fine-grained reward signals.
Right, the dense reward part. Getting more than just a binary success or fail at the end of a long trajectory. That's crucial for faster learning. But I'm still skeptical about the diversity of synthesized failures. Real-world failures are often unexpected and hard to predict. Can a synthesis algorithm really capture that long tail effectively?
That's the million-dollar question, Sam. Can you model the true unpredictability of the physical world synthetically? They claim it significantly improves policy learning, so they must be onto something in terms of generating useful failures, even if it's not every possible failure.
I mean, if it allows them to iterate faster and explore a broader range of negative examples, it's still a win. It just highlights the continuous struggle to bridge the gap between simulation and reality.
Which brings us nicely to PalmClaw, a native on-device agent framework for mobile phones. This is another piece of the puzzle for localizing power, Sam. LLM agents running natively on your phone, not just interacting with a cloud API.
Okay, this is actually pretty big. We've had mobile agents before, but they usually operate through GUI actions like tapping and swiping, which is clunky and easily breaks. A native agent framework means it's talking directly to the phone's OS and apps.
Exactly. It's about moving beyond simulating a finger on a screen to having the agent directly access the phone's sensors, data, and applications. Think about the privacy implications too, Sam. If the agent is running locally, your data isn't constantly being sent up to a server.
That's a huge privacy benefit, you're right. And the speed. No network latency for every action. But this requires some significant on-device model optimization, doesn't it? LLMs are still quite large, even small ones. How much can a phone handle without melting in your hand?
That's the technical hurdle they're addressing, and it circles back to our initial point about pushing efficiency. They're making these models perform at a level suitable for a mobile phone. It's the ultimate edge scenario, but it's enabled by making the compute unit, the phone, vastly more capable.
So it's not just about a framework. It's about the underlying models being small and efficient enough to run locally without draining the battery in an hour. This changes the game for personal assistants, too. More intelligent, more context-aware, and crucially, more private.
It feels like the natural evolution of the smartphone, doesn't it? From apps to agents, directly integrated with the device's capabilities, not just an interface layer. It's a genuinely exciting prospect, Sam.
It is, Alex. I mean, my phone already knows more about me than I do. Might as well let it put that knowledge to good use locally, rather than sending it all to some cloud provider. That's a win.
And finally, let's talk about FlowWAM, optical flow as a unified action representation for world action models. This paper is all about improving how robots understand and predict actions using visual information, leveraging pre-trained video generators.
World action models are interesting because they try to leverage the amazing progress in video generation for robot control. But the problem, as they state, is how do you represent actions in a way that aligns with those video generators and provides enough motion cues for accurate control? Numerical actions don't work, and visual ones often miss the temporal structure.
Right.
So they propose using optical flow as that unified action representation. Optical flow essentially captures pixel-level motion across frames. It's a dense, visual representation of movement. This allows them to use a dual-stream diffusion framework, essentially to predict actions that are visually coherent with what a video generator would produce.
I see. So instead of telling the robot to move joint A by X degrees and joint B by Y degrees, you're telling it, create this pattern of visual movement. That makes sense for aligning with video generators. It's like teaching it to dance by showing it the flow of movement, not just the discrete steps.
Exactly, Sam. It's a more natural, intuitive representation for vision-based systems, and it means these WAMs can predict not just what the world will look like, but how the robot's actions will make it move, all within a visual, generative framework.
My concern here is the precision, Alex. Optical flow is great for general motion, but for fine-grained manipulation, like picking up a tiny screw, can it provide the exact sub-millimeter control needed? Or is this more for broader, more general actions?
They claim it carries enough motion cues for accurate control, which implies they're addressing that. The power here is unifying the action representation with the world model's visual understanding. If the world model thinks in visual flow, then the action should too. It brings coherence to the entire control loop.
Yeah, it's about closing that loop in the most visually consistent way possible. If you want a robot that understands the world through video, then its action should be understood that way too. It's a very elegant solution to a tricky problem.
It truly is. So when we look at all these, from Terra-Zero simulation speed on a single GPU, to agents learning to be efficient with their context, to on-device LLMs, and then visual action representations, it all points to this drive for extreme efficiency and capability within a contained system.
Yeah, it's like the computing power isn't getting infinitely bigger, but it's getting infinitely smarter about how it uses the power it has. It's less about a new type of hardware and more about unlocking the full potential of what we already have.
Right. It's not about cloud versus edge anymore, is it? It's about enough compute, wherever you are, capable of astonishing things. And I keep coming back to, what does this mean for the future of specialized hardware? If general-purpose chips are becoming this efficient, do we even need as many custom ASICs as we once thought?
That's a big question, Alex. I think we'll always need some specialization, but maybe the bar for what requires it just got a lot higher.
That's it for the Robotics Brief this week.
Thanks for joining us, everyone.
We'll see you next episode. Take care.